Okay, so students, we've been discussing about block ciphers during the previous classes. We'll go into data encryption standard today. So before that, we'll go through a quick recap of what we've been discussing through the past few days. We mentioned about different encryption algorithms, and we did mathematical fundamentals for encryption algorithms as well. And then we moved on into how encryption happens within computers. So we're not doing encryption on pen and paper anymore. We mentioned about what stream ciphers are, depending on how there are various classifications of encryption algorithms. We've done that as well. So depending on how data is being processed, you have the stream cipher and the block cipher. And we mentioned that in stream ciphers you have the input bits being processed bitwise. So a stream of input bits coming in, of plain text coming in, being mapped into ciphertext, and you get stream-wise processing. Block ciphers are wherein typically blocks of plain text are being considered, are mapped into corresponding ciphertext, and blocks of ciphertext outputs are being generated. So we'll discuss about block ciphers with special emphasis on the data encryption standard at first, and then we'll move on to other forms of encryption. We saw how these algorithms work on a block diagram basis as well. So probably you've drawn this figure down. We mentioned about the design principles of block ciphers with special emphasis on what Shannon proposes that every encryption algorithm should possess. So Shannon proposes that a quick recap, Shannon proposes that every encryption algorithm should possess two features, diffusion and confusion, and he also gave us methods on how to achieve diffusion and confusion. He says that we can achieve that through substitution and permutations. So we as a cryptographer should ensure that our algorithm possesses features like diffusion and confusion, wherein one small change in the plain text is going to create significant change in the ciphertext. So statistical parameters of the plain text is diffused into a larger number of bits in the corresponding ciphertext. That's what diffusion is all about. Likewise, confusion is wherein the statistical relationship between the key and the ciphertext are as complex as possible. So typically it just mentions that you should not have statistical similarities between the plain text and the key and the ciphertext. And then we mentioned about the general structure that was proposed by Feastel. Feastel was an employee at IBM, as we mentioned. He gave us a general structure, and he has opened up quite a lot of different parameters for a cryptographer to explore upon. So he gave us these different design features. And based on these design features, we also mentioned about typical structure of a Feastel encryption algorithm. So both DES and AES are going to be extensions of this typical structure. We mentioned about how the decryption works. So decryption is the exact inverse of encryption process. So whatever happens in the encryption, we just have the reverse happening in the decryption side. We also mentioned about how an example works. You saw this. We also discussed that the F function, the parameter over here in this algorithm, the function that somehow maps the key that comes in and the plain text. Okay, so this is the decryption structure. So the ciphertext and the key has to be mapped in some way, the F function as we call it. For the F function, you particularly need not have any particular characteristics on it, but let us see how things work. So we move on to the data encryption standard. Okay, brief history on data encryption standard. It was an algorithm which was later approved by the NIST as a standard algorithm. At times DES. Right now we just locally use DES as a verb. It came in as the data encryption algorithm. It is sometimes referred to as the international data encryption algorithm as well, so please do not get confused with these terminologies. So the NIST had an open call for algorithms to be approved as a standardized algorithm for worldwide deployment, and Feastel, who was working with IBM, had previously designed a Lucifer algorithm for their applications. So the Lucifer algorithm had a block structure which took in 64 bits of block size and used a 128-bit key, which was slightly modified. It got Lucifer himself slightly modified this algorithm and submitted it to the NIST. And among various other algorithms, this Lucifer algorithm got selected. But the slight modification that was made was a 56-bit key being used in lieu of the 128-bit key that the Lucifer algorithm used. And of course, the design criteria was a little bit classified. Now, there were quite a lot of controversies around as of why a lower bit size was used for the keyword. But eventually there were quite a few awareness sessions and other programs being made public, and gradually it became standardized. So, and there was worldwide deployment. The data encryption standard was in use until the late 1990s, which later was replaced by the advanced encryption standard, which is the next algorithm that we will be learning about. So this is the structure of the data encryption standard, or the data encryption algorithm as we call it. So students, you must draw this figure out and know how the steps work. So let's briefly look into how this algorithm works. So as we said, you have a 64-bit plain text block being taken. So you have your entire plain text, the huge plain text, which each alphabet is made into 8 bits of code. So you have 8-bit representations for A, 8-bit for B, 8-bit for C, all the way to Z. And you have the plain text, and from the plain text, the binary plain text, and from the binary plain text you go ahead and pick up 64 bits of the plain text. Now the 64 bits of plain text is taken into a round which you call the initial permutation. Now, as we said, Shannon proposed that substitution and permutation has to be used so that you achieve diffusion and confusion. Take note of that. Initial permutation, we'll see what this initial permutation is. There is some form of rearrangement of the 64 bits happening, and then you go into the round function. So there is one round, there are 2 rounds, it goes all the way down to 16 rounds. So if you remember the design features that Feastel gives us, it lets us choose the bit size, right? So we choose 64 bits in this case. It lets us choose the number of rounds to be used. Data encryption algorithm happens to have chosen 16 rounds of operation. So 64 bits goes into round 1. You get 64 bits of can't say ciphertext at this point of time. So you get each round has a 64-bit input, gets a 64-bit output. Goes into round 2, get 64 bits of output over here. You go into round 3, round 4, all the way down to round 16. You get 64 bits of output here. It goes into a 32-bit swap. Okay, a 32-bit swap. Let's see what it is. And then you still have the 64 bits of output, and then there is the inverse initial permutation. So whatever happened over here, the initial permutation before the 64 bits went into the first round, the exact inverse happens here. So you have an inverse initial permutation, and you have 64 bits of ciphertext coming in. And this process continues until the entire plain text is encrypted. Now let us look at this interesting part on the right hand side here. You have each round taking in each sub key. So every round has a different sub key, and if you remember the design architecture, the design parameters that were left open to the cryptographer, you saw that different round key generation algorithms were kept open for us to choose. That is what Feastel has given us. So the data encryption algorithm uses this particular structure for sub key generation. We start off with a 64-bit key, so 64-bit plain text and 64-bit key. gets permutated. Okay, you call this the permutation choice 1 or permutative choice 1. So some form of permutation happens over here. You have the 64-bit key, take note, gets converted into 56 bits. Okay, so 64-bit key goes in, gets permutated to 56 bits. There is one round of left circular shift. The left circular shift still gives you 56 bits. It goes into a permutated choice 2, which converts the 56 bits into 48 bits. So take special note of this. It is only 48 bits of round key that goes into the round function of the data encryption algorithm. So 64 bits of input goes into the round function, and if you remember the feature structure, the 64 bits is not processed as 64 bits itself. It gets processed as the left half and the right half. Remember that? Right. So you have the 32-bit left half and the 32-bit right half that gets processed with the 48 bits of key at round 1, giving you 64-bit. The 64-bit goes into round 2. So whatever you had at the round 1, you have one more round of left circular shift, giving you the same 56 bits, second permutative choice, bringing in 48 bits into round 2. And likewise the system continues. So at every round you have 64 bits of input going in. Within the round function you have the 32-bit left and the 32-bit right, okay, as in feature structure, and you have from the other end the 48 bits of key coming in. So that is what gets kind of mapped inside the round function. So this is how the general DES algorithm works. Now this is where you get to pause the video and draw out this the algorithm structure onto your notebook. Okay, hope you've done that. And then let's see what happens at each of those rounds. The initial permutation is the first step of the computation. Now initial permutation just reorders the input data. We just have a form of reordering. So you can look very closely at this. So you have one bit here all the way going up to the 64 bits. So 64 bits of input. You see that there is a mapping that goes all the way. The first bit gets mapped to somewhere on, okay, like say you call it 40. So we're not exactly sure because we still have a little bit of confusion over here, but we can find how and what happens. The first bit, whatever data you have in the first bit, it goes into the 40th bit, okay, in the permutation. Whatever you had in the second position goes in as 8 bit. So what do you have the 8? Probably you have something over here, okay. Probably you have some other bit towards the 60th bit or something that comes in as the first bit. So you just have a permutation, so you just reorder the position of bits. This is what happens in the initial permutation. And if you remember, the last step after every after all round functions, you have an inverse initial permutation. So that step you get the exact inverse of what happens over here. And now what happens inside each of the DES rounds? So round 1, go back to the feature structure that you have in your notebook, takes in two halves of data. So you have the 64-bit data coming in. It takes in a 32-bit left half and the 32-bit right half. So as the feature structure describes, the left half of the next round is going to be the right half. So right half does not get processed as such into the left half. The right half of the second round is going to be the left half of the previous round XORed with some function of the previous right half and the sub key. So you need to go back all the way back to the feature structure of the encryption algorithm. So this is what you already have in your notebook. So 64 bits of plain text comes in. The right half of the 64 bits goes in straight as the left half of the next round function. So the left half of the ith round is going to be the right half of the I-1th round of the previous round. Likewise, you have the left half coming in, which gets XORed with the right half and the sub key going through some function f. You're not still sure about what this f is. So there is some round function f taking place between the right half and the sub key. So you have 32 bits, exactly 32 bits of right half coming in with, what was the bit size of DS round key? Exactly 48 bits. So 48 bits of key that comes in over here. So 48 bits gets something to be done with 32 bits, and that is what you get over here as output. Now this is going to be 32 bits. Okay, 32 bits gets XORed with 32 bits of the left half, and that is what goes in as the right half over here. So the right half of the second round is going to be the left half of the first round XORed with some f function of the first round right half with the round key. Okay, so this is how the DES round function works, exactly as the Feastel structure worked. So that is why I mentioned that the Feastel structure is quite very important. So this is what happens inside. The f function takes 32 bits of the right half and 48 bits of the sub key, and there is some operation happening. Now what happens inside the f function? Remember that f data encryption round structure looks something like this. So f in data encryption standard is this block over here. Very beautiful and very simple. Now let us see what happens over here. Again, this is one place where you will have to pause the video and draw the structure down. Okay, hopefully you've done that. Right, now let us see what happens inside this f function. So 32 bits of the right half, right? So 32 bits of the right half goes into the f function. Now inside the f function you have something called an expander. So there is some form of an expansion happening to the 32 bits of right half, getting 48 bits. So the 32 bits gets expanded to 48 bits, and you have the k of 48 bits, the round function k that comes in. The expanded 48 bits of right half gets XORed with the 48 bits of round key that came in from the round sub key generation algorithm. So from you have an XOR happening over here. That 48 bits that get XORed is taken into some form of a substitution box. So this substitution box are standard boxes. We'll have to see what each of these boxes happen, how processing happens in each of these boxes. What happens over here is the 48 bits of XORed data goes in, and the substitution boxes collectively reduces the 48 bits back into 32 bits. So 48 bits, you have 8 boxes, 6 bits each going in. So you have 1, 2, 3, 4, 5 and 6 bits going into substitution box 1. You call that S box 1. The next 6 bits going into S2, the next 6 bits going into S3 substitution box 3, all the way up to 8. So making 48 bits that goes in as input, and from each of the substitution box you have 4 bits coming out. So 6 bits converts to 4 bits, the next 6 bits converts to 4 bits, 6 bits to 4 bits. So 8 6 bits gets converted to 8 4 bits, giving you 32 bit. And then there is again a permutation happening, and you get 32 bits of output. So from the box, the function round 1, you have 32 bits of input going in, gets expanded to 48 bits, XORed with 48 bits of round key function, get 48 bits of some values divided into 6 bits each, goes into substitution boxes, comes out as 4 bits each, 32 bits, again a permutation, and you get 32 bits of output. And this is what goes into the next round. Okay, now this 32 bits goes into the left half, the right half. This 32 bits goes into one side, the next the other 32 bits comes in, so you have 64 bits going into the next round. Now what happens in each of these substitution boxes? So these S boxes over here, Okay, these S boxes over here is what we're going to discuss next. What happens in the substitution boxes? So you have 8 substitution boxes which has to map 6 bits into 4 bits. Now you have 6 bits of data. So 6 bits of data is first considered. You have to first divide the 6 bits of data into, again, 2 sections. You divide it as the first and last 6 bits of the 6 bits. So the first bit and the 6th bit as a combination, and the middle 4 bits. Now these boxes are kind of okay, let us see. Now this is the 5th standard S box. Okay, now the 5th standard S box has quite a lot of data in it. It has a few rows and a few columns. So this is a 4 rows and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 exactly columns. So we have 4 rows and 16 columns in the standard S boxes. Now S for substitution. We just have substitution happening. Now, how is the substitution happening? Now see, the outer bits is what I said. You have 6 bits of data. The outermost bits, so whatever data you have in the outer bits, the 0th bit and the 1st bit and the 6th bit of the 6 boxes gets considered as the row. So if 0 and 1 were the last outer bits of the substitution of the 6 bits that has to be substituted, that goes in as 0 and 1, and whatever comes in the middle goes in as the column. So okay, from this example, tell me, what was the bit that had to be substituted? Exactly, it was 0 1 1 0 1 1, right? So 0 and 1 of the outer and the of the outer bits got selected as the row, and whatever you had in the middle, the 1 1 0 1, got selected as the column. So 0 1 1 0 1 1 gets replaced by 4 bits of data 1 0 0 1. Okay, now that is what happens here. Okay, now let us look at another example. What might be the substitution if you have 6 bits of data that comes in as 1 1 0 0 0 1? Okay, 1 1 0 0 0 1. Okay, let us see how it happens. The outermost 1 and 1 has to be taken. So this is the row that has to be chosen. 1 and 1, the outermost. In the middle you had 1 0 0. So this is the column that had to be chosen. Okay, so this is going to be your output. So for 1 1 0 0 0 1, your output is going to be 0 1 1 0. So each 6 bits that goes into the S boxes gets substituted into 4 bits. Now this is the 5th S box. Okay, now this is the standard 5th S box. Likewise, you have 8 S boxes. So from all of these 8 S boxes, on the same algorithm, substitution happens. Okay, fine. Okay, so let us see what happens. Data encryption standard works on this algorithm over here. You have the F function that kinds of manipulates or XORs, basically XORs and substitutes. So it is this F box here, this box here, that performs this function over here, this big function over here, and it is this S5, this box S5, that performs this substitution over here. Now all this goes into just that one little F box. Okay, now after processing through the F box, you see how the algorithm goes. Now there's one more thing that we need to be very particular about: what happens into the key schedule. So if you remember properly, you have 64 bits of key coming in, permutated, left circular shift. Permutated gives you 56 bits, left circular shift gives you 56 bits, goes through a permutative choice 2 and gives you 48 bits. So that is exactly what happens in the sub-key generation algorithm. So let us see how things work inside over here. So there is again a permutation choice which selects 56 bits. So you had 64 bits which came in and permutated to 56 bits. And the 56 bits gets kind of converted into two 28-bit halves, again quite similar to what the data encryption algorithm works on. And then you have again 16 stages of kind of rotation and subkeys, because each round key has to be generated, right? So you have 16 stages of shifting, and again a second permutation which converts the 56 bits into 48 bits. So each round of the data encryption standard gets in 48 bits of subkeys. Coming to data encryption standards decryption, it is exactly same as the encryption algorithm. Whatever happens from round 1 all the way to round 16 happens in the same way, just that you go from 16 back to 1. So whatever you did from top to bottom in encryption happens from bottom up in the decryption algorithm. Now this is a very beautiful example on what happens in data encryption standard. So because we cannot use binary in the example, as your textbook shows, it shows you the example in hexadecimal. So after the initial permutation, say for example this is your data, your plain text that has to be processed. So you have 5A00, 5A00 as the left half, and 3CF0, 3C0F as the right half. Whatever you have in the right half goes as such into the left half of the next round, right? So whatever you have over here, it goes straight into the left half. So you have 3CF0, 3C0F, it goes in over here, and see the right half of the first round is different. It is okay. What was the operation, if you remember properly? Okay, it was this left half, this right half was F functioned with the key over here, with the round key over here, and XORed, and that result was XORed with the left half over here, and that is what goes in as BAD22845 as the right half of the second round, of the first round. Now the right half of the first round, BAD22845, goes in as the left half of the second round, and same operation goes into the right half, goes over here, some operation, this goes over here, some operation, all the way down till 16 rounds. And after 16 rounds of operation, you see that there is an inverse initial permutation. So whatever happened over here, whatever permutation happened over here, you have the exact inverse happening over here. So this is how data encryption standard works. One very, very important parameter in data encryption standard is what you call the avalanche effect. Now this is what exactly shows how diffusion and confusion takes role in data encryption standard. Right. So data encryption standard requires you to have diffusion and confusion, right? The avalanche effect is, the example would show in what avalanche effect is. What was avalanche effect? As you had learned earlier in your the p-n junction diodes and all those things in semiconductor physics. Okay, something similar to that. Let us see. Two examples are shown. This is with 1 bit change in the plain text. So let us look at this plain text. Data encryption standard, as you have understood it, works on different plain texts. 02468 is one plain text, 1 bit change. Okay, so you have this exact same plain text with just 1 bit change in the plain text. Let us see what happens as you go through each round of the data encryption standard. Okay, so after one round, you see that your output is 3CF03C0FBAD22845 for this particular data. Okay, so this is after round 1 for this particular data. The second line over here shows the output for this data. So 1246 gets encrypted after one round into this particular bit stream. See, there's only one bit change over here. So after one round of operation, you see that there is one bit change. After the second round of operation, you see that there are 5 bits changing. You look through these two data. So after 2 rounds of operation, 5 bits have changed. We just had 1 bit change in the input. After 2 rounds of operation, the corresponding ciphertext has 5 bits of changes. After 3 bits of round of operation, you have 3 rounds of operations, you have 18 bit change. After 4 rounds of operation, you have 34 bits changed. See what happens? By the time you complete your data encryption standard, 1 bit change in the input with absolutely no other difference. The same key, the same round key, the same round key algorithm, everything kept the same. See how different the ciphertexts are. This is diffusion. 1 bit change in the plain text creates a significant change in the corresponding output ciphertext. You see that data encryption standard gives you, and it is Avalanche Effect, that as each round changes, as each round goes up, you have more number of changes happening. So you have diffusion happening as each round goes through. Likewise, this example shows you the exact same plain text with just 1 bit change in the key. So you have the exact same data that goes in, but 1 bit change in the round key, in the basic key, in the first fundamental 64-bit key. 1 bit change, and that 1 bit change gets escalated. It goes on 3 bits of change in the corresponding output. After first round, 11 bits of change in the output. After the second round, absolutely no comparison between the outputs as you go through 16 rounds of operation. So this gives you confusion as well. So Avalanche in DES shows you that after each round you have significant changes happening as you go through. Now let us discuss a little bit on the strength of the data encryption algorithm. Probably, with 56 bits of key sizes, you have 7.2 times 10 to the power 16 different values. So a normal brute force attack shows is very, very difficult on first sight. Well, it was shown in recent years that brute force can work to kind of break this algorithm. You see how complex the algorithm is and how significant strength the algorithm gives you, but still, in 1999 it was shown that within 22 hours you can break the data encryption algorithm, which led to the development of the advanced encryption standard. So in 2001 onwards, almost every standard practice uses advanced encryption standard as the industry standard deployed encryption algorithm. So, but it is very similar to the data encryption standard, so probably proper understanding on data encryption standard will help you as well. How can the data encryption standard be actually broken? There are 2 kinds of attacks for this. You have the differential cryptanalysis and the linear cryptanalysis, and there is also something called the timing attack. Now the timing attack, as you saw the data encryption standard, you saw that different inputs and different keys takes slightly different times for the output to get generated. Now this is when it gets implemented into hardware. Okay, so this data encryption algorithm can be coded into the FPGA and maybe created hardwares, and we did mention about Qualcomm as well, okay, as holding the patent for CDMA in the previous classes. Likewise, data encryption standard can be brought into hardware, and in the hardware, for different inputs, you can notice that there are slight differences in the timing for encryption to process and the output to be received. Now, closely watching the time required for encryption to happen, there are some forms of attacks which we call timing attacks, but it was not actually proven to break DES. but 56-bit key sizes could be broken in kind of 1 hour, okay, of late. And so the 128-bit AES was brought in. So AES can requires at least 5.3 times 10 to the power 17 years to be broken. 26 character monoalphabetic requires 6.3 times 10 to the power 6 years. So you can see that probably this is the most secure algorithm that you have at present, the 256-bit AES. There are kind of applications over the internet that performs 256-bit advanced encryption standard as a standard encryption practice. Another point to note is the government of India requires standardized algorithms of 40-bit key AES. Okay, 40 bits of AES is what the government of India has put in as a standard, but there are almost all applications uses much higher key sizes, so we are quite sure that we are secure. There are quite a few extra slides on how cryptanalysis happens on block ciphers, so on differential cryptanalysis and linear cryptanalysis. I think we shall discuss about these in next video, or probably in the next class. Okay, thank you.